Hi, I'm Bryan Jacobs, a program manager in DARPA's MTO office. I'm excited to be here today to talk to you about some quantum-enabled sensing and information science processing. I'm going to talk about our interests in superconducting electronics. I believe that in order to reach the fundamental limits for sensing, compute speed, and compute power efficiency, we will need something like superconducting electronics. However, there are many challenges to implementing this that relate to designs, materials, and fabrication processes. I'm also going to talk about ideas that we have for trying to revolutionize our understanding in fault-tolerant quantum error correction. This is important because the promises of quantum computing rely on assumptions related to the ability of fault-tolerant quantum error correction to make large-scale systems. So I'd like to briefly talk about all of those things today. So first, I'd like to talk about the prospects for superconducting electronics to do sensing and processing. What is shown on the left is something that is known as a superconducting quantum interference array. So the circles are what are typically known as SQUIDs, or superconducting quantum interference devices, but these are special ones. They actually have 3 Josephson junctions. The extra Josephson junction is there in order to make these more linear devices. What we have theorized about these devices is that you could actually achieve very wideband, very sensitive electromagnetic sensing with them. Roughly speaking, when you put these different loops in series, you increase the voltage that comes out of them. When you put them in parallel, which you can do simultaneously, it increases the current that comes out of them. So your sensor array, in this case, becomes your low noise amplifier. And since this is all operating at 4 degrees Kelvin, we're at the thermal noise limit. So we have the prospects for this. However, there are many challenges associated with trying to demonstrate this kind of performance because of the sensitivities to all of the different design parameters, which relate to the different diameters in the loops, which is what gives you bandwidth sensitivity and helps overcome what is frequently known as the Chu limit for passive antennas in terms of their bandwidth performance. We hope that we can do this in superconducting electronics without having to go to complicated non-Forester circuits that also have their own limitations. Okay, what if we have the ability to look at 50 gigahertz of the EM spectrum in one small 2 centimeter square device? How can we process it? If we wanted to use conventional CMOS electronics that are operating at a much lower rate than let's say a 50 gigahertz sampling rate, we would have to interleave a number of these analog to digital converters, which would typically mean we'd need a rack of electronics to just gather the signals from one of these sensors. Now, in superconducting electronics, we know that we can actually make very high speed, 100 gigahertz type analog to digital converters using something that's known as single flux quantum logic, which is what is shown on the right. Now, the challenges, these have been demonstrated at very high rates. The primary challenges relate to some of the idiosyncrasies with designing superconducting logic circuits, which I'll talk about in a minute. But the fundamental challenge right now for getting this ADC technology to scale would be to design a, let's say, 14-bit analog to digital converter that isn't exponential in the number of components, i.e. less than 2 to the 14 components in order to do 15-bit resolution at, let's say, 50 gigahertz. If we have the signals that have been converted into digital form, how are we going to process them? Conventionally, we would need a rack of computers to process all that information at the rate it's coming out because of the limited clock rates, which have been essentially stagnant due to the Dennard scaling for the last 10 plus years. Superconducting logic also offers us the ability to overcome that challenge with general purpose HPC compute capabilities. However, there are challenges related to that primarily in the integration densities. So right now, superconducting logic is about a factor of 10,000 behind state-of-the-art CMOS 10 nanometer technology. How can we overcome this? Well, the processing speed promised by superconducting electronics brings us down to within a factor of about 100 with CMOS. To get closer, we would need to re-envision or reimagine exactly how we're going to do some of the critical features in the superconducting electronics technology, namely the inductors. So this type of technology is dominated by inductors as opposed to CMOS technology, which is dominated by capacitors. So the issue is the inductors are big. One of the reasons they're big is because the loops for the inductors need to be a certain size to maintain a critical current in the circuit. Now, one of the ways that we imagine that we can shrink the area is if we actually increase the thickness of the Josephson junctions that are the intrinsic elements in this type of compute technology. And by increasing the thickness, we would expect to gain robustness to fabrication variations. It's these fabrication variations that are currently also limiting the yield from these types of devices. So by a number of different techniques, different materials, different tools, different fabrication processes, we would hope to get the superconducting technology to within about a factor of 10 for the performance density of CMOS, which, because it's also in the same cold environment, we would be able to leverage the size, weight, and power of the type of small, compact refrigerators that are necessary to maintain those temperatures. Now I'd like to shift gears a little bit and talk about fault-tolerant quantum error correction. So, as I mentioned before, the promise of quantum computing is enormous. The challenge is equally enormous. And one of the reasons for that is that we have to protect these systems from errors. But in order to do that, we have to make measurements which would tend to be counterproductive to the computation. So the way that's typically done is by encoding what's known as one logical qubit into, let's say, thousands of physical qubits. However, when you look at a quantum system that has even more than just, let's say, 50 qubits in it, it gets to be mathematically intractable to model and simulate the performance of that aggregate of quantum bits. So we currently are stuck in a position where we have many assumptions that go into the analysis of fault-tolerant quantum error-corrected circuits. And we have many different models. One of the things that I would like to see is how we can make a generalized framework for this type of modeling where we can enumerate all of the assumptions. Some of them are implied and not actually recognized at the moment, but we want to enumerate the assumptions and then we want to validate them. And so to do this, I would see a number of different things that are required fundamentally. We want to go from the physical process models to see how the noises get transformed into errors. So noise and imprecision in your control get transformed into errors, and to try to do this in a scalable way. So this would require a number of different innovations. Could be state vector type simulations with importance sampling, and a whole host of other possible mathematical techniques that can help us bound our uncertainty in the performance of these fault-tolerant quantum error correction circuits. So, in summary, I think we have really great prospects for making significant advances in superconducting electronics over the next 5 years. I think we have an equal opportunity in really understanding fault-tolerant quantum error correction and reducing our uncertainty. And the importance of that can't be understated, because essentially estimates of how big a quantum computer would need to be and how long it would take to solve a problem are intricately related to all of the assumptions that go into your fault-tolerant quantum error correction model. And this is what we need to understand better. So if you have interest in any of these subjects, and more importantly, if you have a vision on how to implement some of these, we would love to hear from you. We would love for you to consider joining the DARPA team to bring some of these technologies, which may look like science fiction, but hopefully will deliver in real science in the near future. Thank you.